afternoon everyone. I am Chanda Devnath, one of the PMRF fellows of ISER Berhampur. I am pursuing my PhD in organic chemistry and mainly in organic synthesis and catalysis. So I am the TA of this course instructed by Professor Shamik Nanda from IIT Kharagpur. So in this course I usually discuss about some important reactions which may help you to plan any retrosynthesis of any compound. So in the previous classes I have already discussed some important name reactions. Some reactions involving some other reactions involving olefin and olefin synthesis reactions. So today we will discuss about some thermal and photocatalytic reactions. Till now, whatever reactions we have discussed in this, we need any reagents. The reactions require a reagent. Based on the reagent and the condition of the reaction, we hypothesize that okay, this substrate will go through this type of mechanism. Suppose a reaction has in the previous questions we have already said, if reaction has a PPSC and diethyl azodicarboxylate and a alcohol, we usually go for the Mitsunobu reaction. Like this way, we based on the reagents and the reaction condition, we plan what will be the product. Now there are some reaction which does not require any kind of reagent. Just in presence of heat or light, it can undergoes a reaction and give us our desired product. So this reaction has a huge importance in recent organic chemistry because as no reagents has been required, so that is economically economically friendly, so it can be applied for industry in a large scale synthesis because you do not require any kind of reagents. Moreover, as most of the reactions in this type of thermal and photochemical reaction, most of the reactions are atom economic, means the substrate, the molecular weight of the substrates and molecular weight of the product are usually same. Thus that means there is no generation of byproduct, which is also important because whenever there is a no byproduct is generated, it is more applicable for large scale synthesis because there is no wastage in our reaction. So today we will discuss all these reactions like Diels-Alder reaction. I think this is familiar to everyone. There are some other reaction like Barton-Nitrile photolysis reaction, Barton decarboxylation, Barton-Maccombie deoxygenation, Ireland-Claisen in reaction, Konya in reaction, Claisen rearrangement and Cope rearrangement. So let's start with Diels-Alder reaction. So I think Diels-Alder reaction is familiar to most of us. In Diels-Alder reaction, a 1,3-diene reacts with a dienophile to form a 6-membered adduct. In this case, we lost 3 pi bonds. Instead of that, we generates 2 sigma bond and a pi bond. With the loss of 3 pi bonds, the newly generated 1 pi bond and 2 sigma bond. So this is the regio selectivity. If there is an electron donating group at this position, then electron movement is kind of like this way, which generates a negative charge at this center. And if there is electron donating group at this position, the electron movement will be like kind of this way, and generation of negative charge will be at this point. Whereas if we have an electron withdrawing group on our dienophile, then there will be partial positive charge at the beta position. So whenever we want to combine, so most of the cases we need a electron donating group on our diene and a electron withdrawing group on our dienophile. Here I haven't drawn that. If you want to know in more details, you can go to Caduthers. There is a whole chapter on this Diels-Alder reaction. You can go and check from there. In Caduthers they have mentioned that for a faster Diels-Alder reaction, the energy gap between the HOMO-LUMO should be reduced. Means we know the activation energy. So there is a HOMO band and there is a LUMO band. So the energy gap between these two should be reduced in case of Diels-Alder reaction. Now this HOMO comes from the diene. This HOMO comes from the diene. HOMO means highest occupied molecular orbital. And this LUMO comes from dienophile. And LUMO comes from the dienophile. And LUMO comes from the dienophile. Now, if we add any electron donating group, the energy of the HOMO increases due to electrons, so the energy of the HOMO increases. So suppose before this is like this, after adding a electron donating group, the energy of the HOMO increases, whereas if you add a electron withdrawing group, the energy of the LUMO decreases. So the energy gap between this HOMO-LUMO is reduced. So in this case, so if we have electron donating group in our diene and electron withdrawing group in our dienophile, we can get this product. If there is a and if we have an opposite one, suppose if we have an electron withdrawing group in our diene and electron donating group in our dienophile, this is called retro-Diels-Alder reaction. This is called also retro Diels-Alder reaction, because we are just switching the groups. We are using the electron withdrawing group on the diene and electron donating group in the dienophile. In that case, we will get this kind of product. Now, what will be the product in this reaction? So we have to do the electronic movement. So let's first check where is the negative charge. So this is our Cn. So Cn has a electron withdrawing effect. So there will be a partial positive charge at this position. Whereas the OMe is too far from this two double bond, so that's why it's not that much effect. But if we have a so the product will be so always in case of Diels-Alder reaction, there will be a formation of 6-member ring. Initially, there is a formation of 6-member ring with a double bond, a cyclohexadiene. This will be our product. Now what will be product in this case? If you show the electronic movement, be kind of like this. And there will be delta positive charge here. So the delta positive and delta negative will combine to itself. So the correct option will be, so the correct answer will be, there will be a formation of 6-membered ring. This will be our correct. Okay. So this question came in GATE 2016. What will be P and Q? So first, from the substrates you can see it, and there is no reagent is given, only heat. So that it will go through a Diels-Alder type of reaction for P. So let's first draw the P. What will be our P? So if we show the electronic movement, then there is a negative charge here. So there is a negative charge, therefore so it will combine like this way. So there will be a CN and OAC. So in the next step, if you add excess NaOMe in presence of methoxide anion, this SiMe3 will be deprotected. As well as it will attack this center and substitute CN. In the next step, this will be also eliminated, the OAC will eliminate from the system, and there will be ketoenol tautomerism. So the two keto group will be opposite to each other. So the correct P will be this one. So A and B are already cut. The correct option will be between C or D. Now we have to see what will be the next step. So this will be our P. In the next step, PHMG we are We'll attack now. Both of the carbonyl are same in nature. So PHMGPR will attack one of the carbonyl. Suppose it is attacking here. Now in the next step, in presence of, there will be elimination of water. Now there is a proton here at this bridgehead position, and also there is a proton here. So which will be eliminated? Obviously this one, because we know from the Braid's rule, a double bond at the bridgehead position is not stable. Double bond at these bridgehead positions are not stable. So this proton will be eliminated. So the correct option will be this one. So the C. Okay. Let's go to the next one. What will be our compound A? This reaction we have already discussed. Whenever there is a tin and palladium has been used to combine them, that means this is a coupling reaction. Which type of coupling? This is a steel coupling. Whenever tin is used as a transmetallitic agent, that is called steel coupling. So what will happen? Just simple. There will be a coupling reaction. This carbon will couple with this carbon in presence of palladium. So the correct option will be this is our correct answer. Now if it undergoes a conjugation, it gives us compound B. Now in this compound B will undergoes a Diels-Alder reaction with this act as a diene, and this will act as our dienophile, and it will undergoes a so it will attack here. Okay, so it undergoes a Diels-Alder reaction. So the product will be this one. Like this way, just mixing Diels-Alder with another type of reaction, we can get an idea, predict a synthesis of a new product. So what will be the mechanism in this case? They have given the substrate and the product. What will be the mechanism in this case? So they have given the product and also are shown that there will be elimination of carbon monoxide. There will be elimination of carbon monoxide. So let's draw so from this structure, if and no reagents is given, just heating. So that means it will undergo the 4+2 cycloaddition reaction. That 4+2 Diels-Alder reaction. So as this dienophile is equivalent from both the sides, so the combination can be anyhow. Whenever the dienophile or diene are equivalent, then diene is not equivalent, but dienophile is equivalent. So we don't have to consider the electronic movement. Just we have to cycloaddition of, we have to draw the cycloaddition product. Whenever the dienophile is not equivalent from both the sides, suppose there is a different group here and different, then we have to consider from where the electron density is less or where the electron density is high, so that we can combine both the diene and dienophile to prepare the 6-member ring. But if the dienophile is equivalent from both the sides, that means the electron density on both the sides is equivalent, so there is no question of to draw the how the electronic movement is taking place at this case. So if it moves like this way, so what will be the product? There will be formation of 6-member ring with a double bond here and 2 CO2 group. So now to gain the aromaticity, there is only 2 double bond. To gain the aromaticity we need another double bond. To gain the aromaticity we need 6 double bonds. So if the electron moves like this way, this comes here, so then it will give us this aromatic ring, while there will be elimination of carbon monoxide. Okay. Now what will be the product in this case? Because the diene and dienophile both are equivalent from both the sides, so we don't have to consider the electronic movement. Just there will be formation of 6-member ring. Okay, let's go to the next topic, that is Barton nitrile photolysis reaction. So the previous one, Diels-Alder reaction, is usually catalyzed by thermal condition. We need a high temperature. In high temperature the reactions take place. What will happen if this reaction takes place in presence of light? So Barton reaction is a reaction known as a Barton nitrile ester reaction, a photochemical reaction. For this discovery, Professor Barton got a Nobel Prize in 1969. So due to unique property at the time to change otherwise inert substrate, Barton used for the reaction. So we know that substituting an alpha and beta positions are bit simple by adding through enol esterification or anything. The substitution at alpha and beta position is quite easy, but substituting a delta position is not that much easy for chemist. So that's why by this pathway we can substitute a delta position of a simple carbocyclic chain. So wherever the nitrous oxide is there, with respect to that the delta, whatever the delta position is there, that will be reacted under the reaction condition to give us this product. So what is the mechanism? Barton reaction involves the homolytic cleavage of this alkyl N oxide followed by a delta hydrogen abstraction, generation of a radical, then recombination of the radical and the N oxide radical, then through tautomerism it gives oxime. Selectivity for the delta hydrogen is a result of the result of formation of a 6-member transition state. So why we are going for the delta hydrogen only? Because see, whenever we are taking this delta hydrogen, the transition state becomes a 6-member transition state, that is a Zimmermann-Texler transition state. So whenever any reaction goes through a 6-member transition state, they are kind of stable. That's why it has selectivity to the delta hydrogen. If it would take any hydrogen from gamma position or beta position, it won't make a 6-member transition state. Just to make a 6-member transition state, selectivity goes towards the delta hydrogen. So there is an application. So let's see what is the mechanism behind this. If you have a OH, then if you add NaCl, it will undergo form a N oxide. In presence of light, it undergoes a Barton nitrile photolysis reaction, where it undergoes a homolytic cleavage and alpha delta position. A delta position with respect to this OH will be, delta hydrogen will be taken up and a radical will be generated at this position, and this radical will combine with this nitroxide radical. Another probability is alpha. So there are two types of delta hydrogens. So which will be taken up? So if you see, there are two delta hydrogens are possible. So if you see, this portion is more sterically crowded than that of this one, because it's inside the ring, it's inside the between the 3 6-member rings. So this is more sterically crowded than this one. So that's why this proton will be taken up and radical will be generated here. It will combine with our nitrous oxide, and through tautomerization it will give us this oxime, and in presence of NaNO2 it undergoes a cyclization to give us this as our product. Okay, so if you have a multiple delta hydrogen, you have to go for that delta hydrogen which is sterically less crowded, so that our 6-member transition state will be less sterically hindered. Next is Barton decarboxylation reaction. The Barton decarboxylation is a radical reaction in which decarboxylic acid is converted to a thiohydroxamide ester. The product is then heated in presence of radical initiator and a suitable hydrogen donor to afford the decarboxylated product. This is an example of reductive decarboxylation. Using the reaction, it is possible to remove the carboxylic acid moiety from any alkyl group and replace them with a functional group. So in presence of this it undergoes esterification, forming this, then it undergoes a homolytic cleavage, and through elimination of carbon dioxide it forms R dot, and this R dot will combine with any radical. Here we are giving a hydrogen radical, that's why it combined with this and give us a alkane. Instead of hydrogen radical, if you give any other radical source, it can combine with that one to give us this homocoupling product. So this is our mechanism where this ester undergoes a homolytic cleavage to give this R radical. This R radical, and in here in this case as we are giving this BU3SNH, which is hydride radical generator. It will give a H dot. It will combine with our R dot and give us this alkane as a product. Instead of BU3SNH, if we add a bromine, then it can combine with our bromine, give us a alkyl bromide. So just by changing the reagent, we can get a substituted product or substituted alkane. Next question is Barton-McCombie deoxygenation reaction. So Barton-McCombie deoxygenation is an organic reaction in which hydroxy functional group in an organic compound is replaced by a hydrogen to give an alkyl group. So similar to the decarboxylation reaction. There, as carbon dioxide is released, so that's why decarboxylation reaction. Here the no carbon dioxide is released, just OH group is there, so it undergoes a esterification with this thioester, and then through homolytic cleavage and R dot is generated, which combines with this radical source and give us this alkene. So this is similar to the so Barton is similar to the Barton-McCombie reaction, Barton decarboxylation reaction. In the difference is just there is reaction is the starting material is carboxylic acid, here the starting material is alcohol. There is a generation of carbon dioxide, there is no generation of carbon dioxide. You have to relate the mechanism so that just by remembering one of them you can go solve many questions. Just see the difference in the mechanism. Next is 3,3 sigma-topic reaction. So there are various type of 3,3 sigma-topic reaction. I have mentioned some of them which are important and in the questions from which usually come in our examinations. So first one is Cope rearrangement. So it is extensively studied in organic reaction, 3,3 sigma-topic reaction, where we have this type of compound. So this is in presence of heat, it undergoes a 3,3 sigma-topic reaction. It goes through a 6-member transition state like this. It goes to a 6-member transition state. Goes to a 6-member transition state. Okay. The next one is Claisen rearrangement. It is similar to the Cope one. Just in this case of Cope, the carbon-carbon bond cleavage takes place. But in case of Claisen, the carbon-oxygen bond cleavage takes place. So heating of allyl vinyl ether will initiate this 3,3 sigma-topic rearrangement to give this gamma delta unsaturated carbonyl given by exergonic favored carbonyl carbon monoxide bond formation. Next is Ireland-Claisen rearrangement. It is a chemical reaction of an allylic ester with strong base to give an gamma delta unsaturated carboxylic acid. All these are similar to the Claisen reaction, just varying the one group a little bit. We can undergo this type of reaction. Next is Overman rearrangement. This is also a Claisen type of rearrangement where this OH will combine with this CN, form this imine. So instead of carbon-carbon bond, one bond is carbon-carbon nitrogen double bond, which undergoes a Claisen type of reaction. So instead of Claisen, in case of Claisen this is a carbon-carbon double bond, but in case of this Overman reaction this is a imine bond. That is the main difference. So you have to notify the what is the difference, but the mechanism for all of them are same. So you have to just move the electron like that way. If you can give a numbering, it will be very easy for you. Whenever there is a two double bonds like this way, so give this numbering as 2, 3, 1, 1. So this is a sigma-topic reaction. Always try to solve through a 6-member transition state. It will avoid any mistake in stereochemical aspect. So always try to draw through a 6-member transition state. This is the mechanism, as I have already told. This is a movement of electron to give a 6-member transition state to give us this as our product. So this is an example. How this, so here instead of double bond, instead of single bond, there is a 4-member ring. So when this cleavage takes place, there is a ring expansion and give us this 8-member ring. So what will be the product in these two cases? So first one, by seeing the reagent, you can see this is a Barton NPTEL photolysis reaction. Barton NPTEL photolysis reaction. So what will be the product? I just give 2 seconds. Just think what will be the product. I have already discussed. Just we have discussed it. So let's see. So this will first combine with this and eliminate this, substitute the chlorine. So let's count the alpha position, delta position. So which is less strain position with respect to this alpha position? Obviously this one, because all are inside the ring, so there will be a huge strain to form a 6-member ring. This is a less strain position. There will be a formation of oxide. Okay, let's go to the next one. What will be the product in this case? So this is a kind of Barton-McCombie reaction. So it will undergo the esterification first. It will react with this one, whereas this it will react with another molecule, undergo the cleavage. There will be a generation of radical at this position and at this position. These two radical as there is already a hydride source is given, so these two radical will be hydrogenated, give us this radical will be hydrogenated. Okay. Next question is this one. Only heat is given. So what will be? So there is no kind of nitrous oxide is there. So that means there is no question of Barton type of cleavage. And for Barton, always require a photocatalytic reaction. So we need a light for that. There is no light is given, only heat. So in presence of heat, one option is Diels-Alder reaction, another option is Claisen rearrangement or Cope rearrangement. If we see, is there is possible for Claisen rearrangement, let's do the numbering. Claisen or Cope. If you see, there is a possibility of, if you can give a numbering like this way, 1 1 along the single bond, 2 3 along the adjacent double bond, then there is a possibility of Cope or Claisen rearrangement. So the correct option will be there is 6 membered 1, 2, 3. So it will give us this as our product, where this okay. What will be the answer in this case? Among these 4 options, what will be the correct option? So it, for a hint I give, this will undergo the Claisen type of rearrangement, but here the Claisen moiety that which is required, that is not in the form. There are 2 compounds which will combine to give us such a compound which have that Claisen type of moiety and undergoes a Claisen rearrangement. So can you guess how is this possible? So first, in this case, in presence of H2SO4, this OMe will be protonated, give up H plus. So this OMe will be protonated. Now this OH will attack and this will be eliminated. So there is a combination of the next step, as the acid is still in the medium, so another molecular OMe, that will, this will be also protonated. This OMe also will be protonated. So this H comes here, it eliminates the methanol from the system. Now see, this system is kind of similar to you. So this looks like similar one. This looks like the simple Claisen type of substrate. So they just give the numbering 1, 1. We just give the movement of the electron. So the correct option will be, there will be a carbonyl here. There is a formation of new carbon-carbon bond and the double bond will be shifted. So the correct option will be option 4. This is the correct option because there is a carbonyl. Let's see the similarities. There is a carbonyl, there is a formation of here to here, there is a formation of new bond. This is a new bond form. Next, the double bond will be shifted, this double bond will be shifted, and there is a isovocal group. So the correct option will be this one. So in this way, they can give 2 substrate, and you have to synthesize the Claisen adduct, and that will undergoes the Claisen rearrangement. So here they have already formed the Claisen adduct. You have to show what will be the correct option. Now whenever this type of Claisen rearrangement is given where the stereochemistry is concerned in the product, whenever the stereochemistry is the concern in the product, you have to show the stereochemistry of the product. In that case, always go through a 6-member transition state, that is Human transfer transition state, because then you can avoid any mistake in the stereochemistry. So you have to maintain the stereochemistry of the double bonds. Okay. So this double bond has no such stereochemistry because both are bromine group, but this has a trans stereochemistry. So as the OH oxygen is here, so you have to maintain the trans. The isopropyl will be like this way. Okay. So always go through so that you can maintain the stereochemistry. So here the double bond is trans. So to maintain the stereochemistry, we are placing this isopropyl group like this way. Now let's do the Claisen rearrangement. So this electron, so this will move here. So in the product, there will be formation of carbonyl moiety. There is formation of double bond. These two bromine, as both are bromine, so there is no such stereochemistry in this case. Here, see what the stereochemistry shows. The isopropyl group is towards the down the plane, towards the below the plane. The isopropyl group is towards below the plane. So the isopropyl stereochemistry will be below the plane. Okay, see how the easy it become. So the correct option will be option B. The correct option will be option B. Why not A? Because there is a not, this is as aldehyde, not ketone. Sorry, not B. The correct option is option C. See, the options are so close to each other, so that's why I just. What is the difference between B and C? There is an isopropyl group and where there is a methyl group. Correct option is option C. So like see, if you go through a 6-member transition state, become very easy. As this isopropyl group is towards the downward, then that's why it's showing below the plane. If it was towards the upward, then it should show above the plane. What will be the product in this case? So as it is a Claisen reaction, we will go through a 6-member transition state. So in presence of LDA, first let's go to the, in presence of LDA is a base, so there is a alpha proton here. So it will take this proton, it undergoes a enolization. So it becomes a double bond here. So there is a double bond here, so it becomes a structure for the Claisen reaction. So let's draw through a 6-member transition state. So if it becomes OLI, then and a double bond here, just imagine there is a double bond and it becomes OLI. Then this OLI and this methyl are in the same plane. So if you, as the oxygen is at this showed like this way, so OLI will be go here, and OLI and methyl are in the same plane. So this methyl will be drawn like this way. The next, this part, there is a double bond here. No stereo double bond. So but there is a ethyl group. Okay. Now let's do the Claisen the correct option is, let's do, if we draw it in a, so what will be the product? There is a carbonyl with OLI. As this methyl is down the plane, towards the downside, so it will be down the plane. So now in presence of H plus, this will be protonated. So the so the structure will be the correct option will be option B. Correct option will be option B. Let's go to the next one. What will be the product in this case? So first there is a alcohol and Cl. They have given Et3N, so it will undergo the esterification reaction. It will undergo the esterification reaction. So this, in presence of Et3N, this will be deprotonated and this OH will attack, oxygen will attack to this position and it will be eliminated, forming a ester. Now in the next step, in presence of LDA, there will be a enolization. So it will be like this. So you have to maintain the stereochemistry here, that double bond is trans. So keep this trans, this ethyl group will be like this way. Now if we just combine this, so the product will be as this ethyl group is upward, so ethyl group will be above the plane. Next, this, as this isopentyl group is downward, so it will be below the plane. Now in presence of H3O plus, this will be protonated, so the correct option will be, correct option is option D. The correct option is option D. Okay, just see the difference between B and D. There is not carbonyl group is here, but we need a carbonyl group, so the correct option is option D. Okay, so next is in reaction. So I hope we can solve any Diels-Alder reaction if comes, because we have solved the very critical ones. So from this idea, whenever there is a Schlezen reaction, just go through a 6-member transition state, then there will be no confusion. Next is in reaction. In organic chemistry, the in reaction is a chemical reaction between alkene with allylic hydrogen and a compound containing multiple bond in order to form a new sigma bond with migration of in double bond. It's similar to the Diels-Alder reaction. In case of Diels-Alder reaction, we have two pi bonds and two diene combined with the diene. These two pi bonds combined with one pi bond. But in this case, one pi and one sigma bond is combining with another pi bond. This is the difference. Just see the difference. In this Diels-Alder there is a double bond, but in this case there is a sigma bond. So this is the mechanism where this is a sigma bond and it undergoes similar type of 6-member transition state. There is an example of in reaction. There is a dienophile. It combines with this to form this as our product. So what will be the product in this case? What will be the product in this case? So you have to see. Okay, there is a proton here. So it can undergo the in reaction. So as this, there is a positive charge at this position, delta positive charge. So this will attack to this position. It will take the proton. So the correct option will be so this will be our product. In this next case, so it will undergo a in type of reaction. So this is similar, this is equivalent diene, so you can go anyhow. There will be generation of double bond. This is methyl group here. Okay. Next is Konya in reaction. So in the organic chemistry, the Konya in reaction, all these reaction name I think you have got in your assignments. That's why I am mentioning all these things, so that you can differentiate what are, and you can pick the correct option in your. If you check your assignments, all this reaction has been given as your options for different questions. In organic chemistry, the Konya in reaction is an intermolecular cyclization reaction between an enolizable carbonyl such as ester and ketone and an alkyne, giving a cyclic product. So this is a Konya in reaction. So what will be the product in this case? So it is just cyclization of this alkene with this alpha position of this carbonyl compound. So what will be, just if you just draw the product, this part will combine with this alpha position, so that there will be a there will be a cyclization. In the next step, in the next one, there is a triple bond here, so it will undergo the cyclization with this alpha position, giving a 5-member ring. The double bond. Okay. Next, and this is the last one, we have to we have to plan the retrosynthesis of this compound from these two substrates by using Diels-Alder reaction. By using Diels-Alder reaction. How can plan? So as they have said that this is a Diels-Alder reaction, if we draw the retrosynthesis of this one, so as it is Diels-Alder reaction, if we just cut these two bonds, then the let's go step by step. First there is epoxidation. If we just remove the epoxidation can be taken place for a double bond easily. So if we just remove the epoxidation part, there will be generation of double bond. Now there is a cyclohexene ring. Cyclohexene means the chance of Diels-Alder reaction, because cyclohexene always the product of Diels-Alder reaction is cyclohexene. So if we just break these two bonds, it can move to here. Then there will be generation of diene. As both are below the plane, so that means both are at the same side. Whereas this diene, one is below the plane, one is above the plane. That means the diene is trans in nature. Both will be in the different plane. One group is below the plane, one group is above the plane. From that side, that's why these two are trans. So this is similar to this one. So we have got one substrate. We have already got one substrate. Now how to prepare this one? How to prepare this one? Because they have just given this alkyl vinyl bromide. How we can prepare this one? So if we just clip from there, then one will be this vinyl bromide. Next one, if we can couple this one with this double bond. So for bromine substitution, we usually use Suzuki coupling. So if we do a Suzuki coupling, we can get from these two. So if you draw the I have drawn the retrosynthesis. If you get in your home, by yourself, try to draw the forward synthesis of this one, so that you can get an idea how the reactions is taking place. As for an idea, I am just giving. First step is Suzuki coupling. First step is Suzuki coupling. Second is Diels-Alder. Second is Diels-Alder reaction. This one is Suzuki coupling, followed by Diels-Alder reaction with this dienophile given. This is provided Diels-Alder reaction. In the next, then we will get this as our product. Now we have a cyclohexene, so one double bond. So if you just perform a epoxidation reaction, the adjacent two ethyl group are below the plane. So if if that creates a steric hindrance, so the MCPP will come from the above the plane. So epoxidation takes place from the above the plane. So the third one is MCPP reaction. It is epoxidation. Okay, so it's simple. For Suzuki, we need this boronic acid and palladium. boronic acid and palladium catalyst. For Suzuki diel solder we just need heat. For diel solder we just need heat, and for this epoxygenation we need this MCPP. Okay, I hope it's clear. Just try to draw the forward synthesis by yourself. So this much for today. Thank you everyone. Have a nice day.